This is my lab 7 for Physics 2211. The main objective of this lab was to create a model using the x and y coordinates of a star to determine the mass of a black hole at the center that has a force on the star and is causing it to move. My main finding was that just using x and y coordinates, one can calculate dp delta p over delta t, which is roughly equal to fnet for delta t sufficiently small enough, and one can use fnet to calculate the mass of the black hole. So I was given the initial position of the black hole, and I was also given the mass of the star, 1.989 times 10 to the 30th, and my time step was the number of seconds in a day, 86,400. So first I calculated the velocity of x in the x direction, and then the velocity in the y direction, and using two velocity vectors that are right next to each other, one can find the change in velocity, but taking those two vectors and multiplying it by the star mass, one can get the change in momentum. So we divide the change in momentum over just the change in time to get dp dt, and since this is a really big system over a lot of space, dp dt is equal to fnet even for that large time step. I also calculated the change in magnitude, so that was just the magnitude of the initial and final momentum, and then I was to take that change over delta t and multiplying that by the direction of the final momentum vector. So that's also equal to fnet, so dp dt parallel is equal to fnet parallel. Dp dt perpendicular you can calculate just by taking dp dt minus dp dt parallel, since the two components add up to get dp dt, and that is also equal to fnet. So to calculate my black hole mass, I just took g, the constant, and then I calculate the magnitude of fnet, and d is just the distance, the scalar distance between the star and the black hole at any given point for the star. And so I just set the magnitude of fnet equal to the magnitude of the gravitational force, since that's the only force that's going on. So it's just fnet, the magnitude of fnet times the distance squared all over the star mass times g. So if we run this, as you see, fnet is going to be pointing towards the black hole, and it gets much larger as it gets closer, so that makes sense. And fnet parallel was parallel to the change in momentum, perpendicular was pointing perpendicular to momentum. So, and I get a mass, and WebAssign accepted it, so I guess it was correct. And it's constant throughout all iterations, so that means that it's correct. So for the what does it mean question, are these related? Well, for delta t sufficiently small enough, fnet is equal to delta p over delta t, or it's approximately equal to as delta t and delta p go to 0. So, and it's also the same for the parallel and perpendicular components. So how are they different? Well, fnet causes delta p over delta t. It's not the other way around. So a change in momentum does not cause a force, so a force causes a change in momentum. But they are equivalent. So can I find a different mass at the same location and still have the star move around in the same motion? Well, I set the magnitude of the gravitational force equal to the magnitude of centripetal force, and since this r is the radius of the kissing circle, it's going to be the same as the r in the gravitational force. One can simplify this expression to get the mass of the black hole, which is equal to the speed squared times the radius of the kissing circle all over g. So if I took the speed times the square root of 2, I should get double mass. And it's easy to check this by adjusting delta t. I just divide delta t by the square root of 2, which increases the speed by square root of 2. Should get double the mass. And as you can see here, I'm getting double the mass. It's consistent. and the force is larger, it's going the same motion.